I welcome you in this lecture on properties of scattering matrix. Well, in the previous lecture, we have seen how the reflected and incident waves at different ports are related to the scattering matrix parameters. Now, figure shows an N-port network. So if we can see that at port 1 we have A1 as the incident wave and B1 as the reflected wave. Likewise at port 2 I have A2 as the incident wave and B2 as the reflected wave. So on up to port N. At port N I have AN as the incident wave and BN as the reflected wave. In the previous lecture what we have seen is that we have seen the reflected waves B1, B2, so on up to BN. They are related to the incident waves A1, A2, so on up to AN by S parameters or by an S matrix S11, S12, so on up to S1n, S21, S22, so on up to S2n, and then SN1, SN2, so on up to SNN. So this corresponds to reflected waves, and this corresponds to incident waves. And this is reflected waves, incident waves. See, I've shown here at port 1, I have shown the incident wave as, for example, by A1. So all the incident waves at these N ports are designated or shown in blue color, A1, A2, A3, A3. This is our A3, so on AN. And the reflected waves at ports B1, B2, B3, they are shown in red color. So the relationship between the reflected and incident is shown here. So the reflected matrix, which is a column matrix, and the matrix corresponding to incident waves is also a column matrix. And in between these two, they are related to each other by what is called as a scattering matrix. So now in today's lecture, we'll discuss various properties of scattering matrix. So let us start. Properties of scattering matrix. So the first property is that this matrix, S matrix, is always a square matrix. So that means for an N-port network, the order of matrices is n cross n, as we have seen above, that for an N-port network shown here in figure, the S matrix has an order of n cross n. So this is the first property. So naturally, if we have a two-port network, so that would mean if I have a two-port network, this as a two-port network, the S matrix here will be of order 2 cross 2. This is port 1, this is port 2. So the S matrix would be a 2 cross 2 matrix. S matrix would be a 2 cross 2 matrix. That would mean it will be having these as elements: S11, S12, S21, S22. Likewise, for a 3-port network, the S matrix would be a 3 cross 3 matrix. So this is our property number 1. Now coming to property number 2. So for a reciprocal network, this S matrix is symmetric. That is, S matrix would be same as the transpose of S matrix. So this is what is symmetry from mathematics. A matrix is said to be symmetric if its transpose is the same matrix. Or we can write as Sij is Sji. That is, ijth element of matrix S would be same as jth element. Here, as I said, St, S transpose, is the transpose of the matrix, is the transpose of scattering matrix S. So as I said, this is true for a reciprocal network, that S matrix is symmetric. Now the question is, what's the reciprocal network? Reciprocal network, as you must be knowing, is a network in which the transmission of a signal between any two ports does not depend on the direction of propagation. Does not depend on the direction of propagation. That is, input and output ports are interchangeable. Input and output ports are interchangeable. So what it means is that, say for example, if I have a two-port network, as say for example I have a two-port network, this is the input port or port number 1, and this is output port or port number 2. This is port 1, this is our port 2. It's a two-port network. Say for example I connect a source here, with power, say for example P1, and I connect a load here, CL, and the power delivered to this load, let it be for example P1 by 2. So I have the input power as P1 and the power that's being delivered to the load is P1 by 2. Now if I for example use the same network, same two-port network, with port 2 here and port 1 here, and if I connect the same source here, the same source is being connected here with power P1, and I connect the same load ZL to port 1. So this is the same two-port network. Only thing is that earlier I was connecting the source at port number 1 and was connecting the load at port number 2. Now what we are doing is that I am connecting the source at port 2 and I am connecting the load at port 1. So I'll again receive the same power P1 by 2. If I receive the same power P1 by 2, that means the network that we were discussing, or the network under discussion, is a reciprocal network. That is, the input and output ports are interchangeable. Now in terms of S parameters, what it means is that S12 should be same as S21, Or for example, for a 3-port network, S13 should be equal to S31. In general, Sij has to be same as Sji for a network to be reciprocal. Examples of, say for example, the examples of reciprocal networks would include transmission lines. Of reciprocal networks, transmission lines, attenuators, circulators, isolators, etc. See, in transmission line, as you know, whether you connect a source on this side or on that side, the power delivered to the load would be the same. Whether you connect source on this side and load on this side, or for example, source on this side and then load on this side, the power dissipated in the load, so as far as the load is the same, would be the same. So transmission lines, even attenuators, so if you connect a source to an attenuator, the loss in the attenuator would be fixed, for example, for fixed attenuators. So in both the cases, whether you connect the source on the input side or the output side on port 1 or port 2, the loss within the attenuator would be the same. Circulators and isolators are also included in reciprocal networks. We'll discuss them separately. Now, circulators and isolators so far are concerned, they are non-reciprocal. These are non-reciprocal networks. So we'll be discussing circulators and isolators as separately. We'll discuss them separately in few lectures in maybe the last lectures. Now coming to property number 3. For a lossless network, S matrix is unitary. That is, S transpose into S conjugate is a unit matrix. Here S transpose ST represents transpose of S. This transpose of S matrix, and S star represents conjugate, rather complex conjugate of S. So complex conjugate would mean if S11, for example, is A plus iota B, then S11 conjugate would be A minus iota B. So this property is for a lossless network. That is, S transpose into S star is a unit matrix, and the order of this unit matrix would be the same as that of the S matrix. So it would be an n cross n matrix. So if S is, for example, a matrix of order 3 cross 3, then our unit matrix I would be of the same order, 3 cross 3. So as I said, this property is for a lossless network. Now, what's a lossless network? A lossless network, as you know, is one which cannot absorb power, which cannot absorb or dissipate power. That means, which means that power flowing into the network or device must be equal to the power delivered to other parts of the network, to other ports of the network, plus the reflected power. So this is what a lossless network means. Say for example, we have a network, we have a 3-port network. Say for example, let us assume that we have a 3-port or an n-port network in general. I have this as port 1, I have this as port 2, and I have this as port 3. So if I have this is port 1, this is port 2 for example, and this is port 3. Now I connect a source here at port 1. I'm connecting a source, and let P1 be the power input. This is the input wave, and then, as you know, we must be having a reflected wave. If it's not matched, then this is a reflected wave. If this port is matched, then in this case there will be no reflected wave. This P would be 0. So we'll be having incident wave only. Let's assume the power input is P1. The power that goes into the network is P1. Now if these are terminated at some loads, port 2 is terminated at some load ZL2, port 3 is terminated at some load, say for example ZL3, then what happens is that the power P1 goes into this, and some portion of this would flow into port 3. If these loads ZL3 is not equal to Z0, ZL2 is not equal to Z0, we'll take two cases. In the one case they are not equal to characteristic impedance. In second case these loads are equal to characteristic impedances, or they are matched loads. This would mean it's a matched load. This is equal to Z0 would again mean that it is a matched load. So we have two situations. I am feeding power P1 at port 1, we are feeding power P1. Now what happens if this is, let us discuss case 2. If it is perfectly matched, there won't be any reflections. That would mean this B, the reflected wave B, is equal to 0 here. And again, if it is port 2 is matched, then again there won't be any reflected wave, B would be equal to 0. So in this case, if it is a lossless network, whatever power I feed here at port 1, some part of the power will be dissipated into port 3, and some part of the power will be dissipated into port 2. Let this be P2, let this be power delivered to load 3 be P3, and power delivered to load 2 be P2. In this case, for a lossless network, P1 would be equal to P2 plus P3. Power input at port 1 is nothing but power delivered to port 2 and port 3. Now if these loads ZL2 and ZL3, if they are not matched, that is this case, if they are not equal to Z0, in this case there will be a reflected wave as well. That would mean B1 is not equal to 0, and here it would mean, this would mean B3 is not equal to 0, and in this case it would mean at port 2 it would mean B2 is not equal to 0. So there would be a wave, a reflected wave at port 2 and port 3. So in this case, power absorbed, power incident at port 1 would be power delivered to port 2, this port 2, plus power delivered to port 3, and the reflections. So this is what I mean by a lossless network. So in case of a lossless network, as I said, it cannot absorb or dissipate power. So power absorbed within this network is 0. Within the network there is no power absorbed or dissipated. It is delivered to the loads connected at different ports. So now if the ports are matched, then the power would completely be absorbed in the matched loads. And if the ports are not matched or not connected at matched loads, then there will be again reflections at these ports. So in a nutshell, the power input at port 1 in this case would be power delivered to the ports plus the reflected power. So in terms of S parameters or in terms of S matrices, we say that a network, that for a lossless network, this condition S transpose into S conjugate has to be a unit matrix. Now let's say, for example, we take an example of a 3 cross 3 matrix. Let S be a 3 cross 3 matrix, means that we have a 3-port network: S11, S12, S13, S21, S22, S23, S31, S32, S33. This is our S matrix. So its transpose, S transpose would be, the first row, as you know, in a transpose would be the first column, second row will become the second column, third row will be the third column. So it will be S11, the first row becomes first column, S12, S13. The second row becomes second column, S21, S22, S23. The third row becomes the third column, the third row, this would become the third column, S31, S32, S33. This is our S transpose. So this is our S transpose. And now let's see the second matrix, which is S conjugate. The S conjugate would be the same matrix as S, except that we have to take the complex conjugates of all the elements: S11 conjugate, S12 conjugate, S13 conjugate, S21 conjugate, S22 conjugate, S23 conjugate, S31 conjugate, S32 conjugate, and S33 conjugate. Complex conjugates of the individual elements. Now if I go by this equation, this matrix would be, as I said, that for a lossless network, S transpose into S conjugate, the product should be a unit matrix. Now if I multiply this S transpose, matrix S transpose, with S conjugate, let us do that. I have S transpose as, or S transpose is S11, S12, S13, S21, S22, S23, and then I have S31, S32, S33. This is our S transpose into S conjugate. This is our S conjugate. So when I multiply it by S11 conjugate, S12 conjugate, S13 conjugate, S21, S22, S23, S31, S32, and S33, this product should be a unit matrix of same order as that of S. That would mean 1 0 0 0 1 0 0 0 1. This is what the product should be. Now when I multiply this row 1, let me use a different color. If I multiply row 1 with column 1, that's, I multiply R1 C1, what I get is S11 S11 star plus S21 S21 star, then S31 S31 star. So I multiply row 1 with column 1, so that would be equal to the first element of the unit matrix. So this has to be equal to 1. So this means I'm multiplying row 1 and column 1. This means, now we know from mathematics that if we multiply a complex number with its conjugate, we get its modulus square. So it would be S11 square, where the vertical line is represent the modulus. S21 square plus S31 square is equal to 1. Likewise, if I multiply row 2 with column 2, now I'll multiply row number 2 with column number 2. If I multiply row 2 with column 2, I'll get S12 star plus S22 star plus S32 star. I multiply S12 S22 conjugate, S32 conjugate, row 2 and column 2. Again, corresponding to this, I have another diagonal element 1. So I can write modulus of S12 square plus modulus of S22 square plus modulus of S32 square is equal to 1. Finally, I can also multiply the third row with the third column. When I multiply third row with the third column, I'll get the third diagonal element, this diagonal element. So that would mean S13, this S13, I am multiplying by this S13 conjugate, this S13, and then I multiply S23 with this S23 conjugate, and finally S33 with S33 conjugate. So that means S13 conjugate plus S23 conjugate plus S33 conjugate would be the third diagonal element, this diagonal element. So that means S13 square, because again I repeat, multiplying a complex number with its conjugate, its modulus square is its modulus square. S23 square plus S33 square is equal to 1. So if we look at these equations, we have these equations, this equation, and this equation. So I can write it in simple summation form as these equations, this, and this. I can write them simply as summation of k running from 1 to n. Here in this case it is 1 to 3. Ski multiplied by the conjugate kj is nothing but 1. So you see, 1 3 with its conjugate, 2 3 with its conjugate, 3 3 with its conjugate is nothing but 1. Likewise, here if we look at this equation, 1 2 conjugate, 2 2 conjugate, 3 2 conjugate is equal to 1. So in summation form I write it as, this is conjugate. So this is how we can represent it. Let me erase this thing. So now, as you know, our S matrix basically is this thing: S11, S12, S13, S21, S22, S23, S31, S32, S33 is our S matrix. And for a lossless network, we have seen that these equations need to be satisfied, or in summation form, we can designate it by this equation, say for example equation 1. So this equation 1 can be written as, so this in nutshell means the sum of, as the sigma indicates that it is the sum of products of the elements, of a particular column, with their corresponding conjugates, is equal to 1. So this is all I'm saying is that S11, S11 star, S21, S22, S21, S21 star, for example, S31, S31 star is equal to 1. So this is what it means. The sum of products of the elements of a particular column. Say, for example, in this case, we have taken this column, S11, 21, 31. When I multiply these elements with their corresponding conjugates, I get 1. So this is what it means. Or it can be stated as the sum of squares, S11 square, S21 square, S31 square. The sum of squares is unity. That means the sum of squares of the elements of a particular column for a lossless network is 1. This is for column 1, for example. Say, for example, for column 2, we can see S12 star, S12 square plus S22 square plus S32 square is equal to 1, as can be seen from this equation. And likewise for column 3, for column number 3, we can see that S13 square, S23 square plus S33 square is equal to 1. That is, the sum of the squares of the elements of a column for a lossless network is 1. So let us try to understand this point. Say, for example, I said for a lossless network, if S is a matrix, say for example for a 3-port network, S11, S12, S21, S21, S11, 12, 13, 21, 22, 23, 31, 32, 33. So what we said is that for a lossless network, S11 square plus S21 square plus S31 square is equal to 1. Or for that matter, for column number 2, this is also valid. S12 square, S22 square, S32 square is also 1, and also valid for column number 3. In general, it is valid for an n-port network. So this time we are considering a 3-port network. Let me try to explain it. Say, for example, we have this as a 3-port network. Let this be port number 1. Let this be our port number 2, and let it be port number 3. So this is port number 1. This is our port number 2. And this is our port number 3. So we have an incident wave. Say, for example, we have incident wave as A1, incident wave here at port 2 as A2, incident wave at port 3 as A3. And the reflected waves as port 1, it will be B1. At port 2, the reflected wave would be B2. And at port 3, it would be B3. So this is a 3-port network, 3-port lossless network. So then if it is a lossless network, then it has to satisfy this equation, S11 square plus S21 square plus S31 square is equal to 1. Now let us see what S11 is. We know S11 is B1 by A1. S11 is B1. Let me use a brighter color. S11 is B1 by A1 square plus S21 would be B2 by A1 square plus S31 is B3 by A1 square. This equation, as per this equation, this has to be equal to 1 for a lossless network. Now this would mean B1 square by A1 square plus B2 square by A1 square B3 square by A1 square is equal to 1. So which in turn means B1 square plus B2 square plus B3 square divided by A1 square is equal to 1, which in turn means B1 square plus B2 square plus B3 square is equal to A1 square. If I divide this equation by 2, That would mean b1 square by 2 plus b2 square by 2 plus b3 square by 2 is equal to a1 square by 2. Now assuming that all the ports are perfectly matched, or connected to matched loads, connected or terminated at matched loads. So if I assume all the ports are connected or terminated at matched loads, all that means is that I'm connecting this by a load, say for example ZL3. I'm connecting this by some load, say for example ZL2. When these ports are terminated at matched loads, that means there won't be any reflection. So here B3 goes into the load and A3 is the reflected wave, so reflected wave would be 0. Here again B2 is the wave that goes into the load and A2 is the reflected wave, so A2 would be 0 as the loads are perfectly matched. Again, when I connect a source here at port number 1, so A1 is my incident, B1 is reflected. If it is perfectly matched here, B1 would be 0. So A1 goes into my network, is the incident wave, and B1 is the reflected wave, assuming that it is a matched connection, so B1 would be 0. So all it means is that A1 square by 2, therefore A1 is the incident wave, as A1 corresponds to incident wave, and as we have seen A1 earlier, A1 square by 2 would be the incident power. Here B2 square by 2 would be the power. B2 square by 2 is the power delivered or dissipated in load CL2. Likewise, if I look at port 3, A3 is 0 but B3 goes into it. B3 square by 2 is the power delivered to load CL3 at port 3. So now if I look at this equation, A1 square by 2 is the incident power or the input power. A1 square by 2 is the input power. Is equal to B1 square by 2, that is the power which is reflected back, but we have assumed proper matching, so B1 square by 2 would be 0. This is 0. B2 square by 2 is the power delivered to load CL2, and B3 square by 2 is the power delivered to port number 3. So all it means is that the power that is being fed at port 1 goes into port 2 and port 3. So this is what it proves. Power input is power absorbed at port 2 and power absorbed at port 3. So there is no power which is being dissipated within the network. No power dissipated within the network. All the power that is being fed at port 1 goes to port 2 and port 3. So this is what it means to be a lossless network, that the losses within the network are 0. So we have seen that for a lossless network, S transpose into S conjugate is nothing but a unit matrix. So this was our property number 3. S transpose into S conjugate is nothing but a unit matrix. Then what we did was that we took an example of a 3 cross 3 matrix or a 3-port network where our S is this and S transpose is this, and then we solved this equation. S transpose into S is a unit matrix I. So in the first case, what I did was that I multiplied row 1 with column 1 to get this diagonal element, and then I multiplied row 2 with column 2, row 2 with column 2 to get this diagonal element, second diagonal element, and then we multiplied row 3 with column 3 to get the third diagonal element. Now what about the non-diagonal elements, this and this? Now say for example I multiply R1 with C2, I'll get a non-diagonal element. I multiply R1 with C3, I'll again get a non-diagonal element. So let us do that as well. So my S transpose into S conjugate is nothing but a unit matrix, n cross n. If the order of matrix S is n cross n, then the unit matrix will be having the same order. Now let me write S transpose again as S11, S11, S12, S13, S21, S22, S23, S31, S32, S33. This is our S transpose, and S conjugate is S11 star, S12, S13, S21, S22, S23, S31, S32, S33. Conjugate, where the star represents the conjugate of each individual element. And then I said this is a matrix, unit matrix 1 0 0 0 1 0 0 0 1. Now, so if I multiply, say for example, S11, this row with this column, for example, I'll get S11, I'll get S11, S12 star plus S21, S22 star plus S31, S32 star, and this time it will be a 0, the right side. Again, I can multiply this S11, this, for example, this row with third row, first row with third column, for example. So I'm multiplying first row with third column. This is first row and this is the third column of the conjugate matrix. So that would be S11, S13 conjugate plus S21, S23 conjugate plus S31, S33 conjugate. And this would be again 0. Or I can even multiply S12, this, for example, this row I can multiply with this column, the third column. In this case, I'll again get a 0 on the right side. S1 to S13 conjugate plus S22, S23 conjugate plus S32, and then the third element here would be S33 conjugate would be 0. So the initial conditions were the right hand side was 1. I was multiplying a row 1 with column. I was multiplying row 1 with column 1. Then row 2 with column 2 would give me the second diagonal element. Row 3 with column 3 would give me the third. Now if I multiply row 1 with column 2, I get a non-diagonal element. I get these non-diagonal elements. So these non-diagonal elements are 0. So I can write this in summation form as sigma k running from 1 to n for an, in general, for an n-port network. In this case, we have taken this example for a 3-port network, but in general, we can have an n-port network, and in that case, k can run from 1 to n. Ski, Skj, the first element and the conjugate of the second element. This has to be 0. And when is it? When I is not equal to j. Now, if we look at this thing, I said earlier on, this Ski into Skj has to be 1 because I am multiplying row 1, column 1, I get this diagonal, row 2, column 2. In this case, when I write this equation, I have to write I is equal to j. And in this case I have to write I not equal to j. If that summation, the earlier summation, was equation number 2, then I can name it as equation number 2. So this in nutshell means, what does this equation mean? This equation can mean the sum of products of any column, sum of products of any column with the corresponding conjugates of any other column is equal to 0. So for example, I had this as the matrix S11, S12, S13, S21, S22, S23, S31, S32, S33 is our S matrix. If I multiply, let me use a different color. If I multiply the first column with the conjugates of the second column, then the product has to be 0. Sum of products of any column with the corresponding conjugates of any other column is 0. That means S11 conjugate of this column would be 0. S11, say for example here, S11, S12 square, S12 star plus S21, S22 star, S31, S32 star has to be 0. Now if I multiply this column with the conjugates of the third column, for example, that again would be a 0. Or if I multiply this column, second column, with the conjugates of column 3, I'll again get a 0. So this is all about the lossless network. So for lossless networks, these are the conditions that need to be satisfied. Now let us discuss the fourth property of S matrix. Fourth property. If any of the terminals / ports or reference is moved away from the junction, or port by a distance ln. This is the physical length ln. The electrical length can be beta and ln. If we multiply it by the phase constant beta and ln, it gives us the electrical distance or the electrical length. Then each Sij involving that port, say for example nth port, will be multiplied by e to the power minus 2j beta and ln. I'll explain it. Let us consider an n-port network. For example, let this be an n-port network. This is our port number 1, this is port number 2, this is port number 3, and let it be port number n. Let me erase it. Let me draw port number n somewhere. Let this be port number 4. This is port 1, this is port 2, port 1, port 2, port 3. Let this be port n, because I have the flexibility of extending this port. Let it be port 3. So all I'm saying is that this property number 4 so far is concerned, is that if we move away from the junction or the port or the reference, then the S parameter gets changed. It gets multiplied by this thing. So all I'm saying is that if I move, say for example I move away from this port by a distance ln, I move away from this port by some distance ln. This is the distance ln. We're extending this port by some distance ln. This is the physical length ln. So if I go by the same logic that you were using, this is port number 1, this is A1 incident wave. I'll use the same colors, A1 as incident wave, and then here it will be A2 as incident wave on port 2, and port 3 A3 as incident wave. Likewise at port N, AN as incident wave. And the reflected wave is by BN, shown in red color. This is B1 reflected wave here. This is B2, the reflected wave at port 2. And this naturally is the reflected wave at port N. It would be BN. Now when I move away from this port N by some distance Ln, the value here, I'll be having a different wave. Let me use a different color. I'll be having, say for example, I'll use this color. I'll be having this as my incident wave, AN dash. If this is AN, this will be AN dash. And if the reflected wave here is BN, the reflected wave here would be BN dash. Now at port 1, say for example, S11 is nothing but B1 by A1, assuming all ports are matched. Likewise, S22 would be B2 by A2. And here at port N, I'll be having SNN equal to Bn upon An. Now when I move away from this port N, I move by some distance Ln, so I'll be having a different S parameter there, SNN dash, let it be SNN dash, which will be Bn dash upon An dash. So now the question is, how is this SNN dash related to SNN? That's the point that we are trying to make. So let's dig into it. Say for example, I have a transmission line. From our transmission line theory, if I have a lossless transmission line of say for example length Ln of infinite length, for example, I have point 1 and point 2 on it, 1 1 dash and 2 2 dash. If the amplitude at point 1 1 dash is An and this length is Ln, the amplitude of the wave at 2 2 dash would be An, same amplitude as it is a lossless line, but only thing is that there will be a phase delay between the two waves. If this is An, if this is some wave W and this is the same wave W, there will be a difference in phase between the two waves. The amplitudes would be the same. So if it is An, it will be An. I'll have to multiply it by e to the power minus j beta ln, where e to the power minus j beta ln corresponds to the phase. So if this is An, this An dash would be simply An, same amplitude, multiplied by e to the power minus j beta ln, where this e to the power minus j beta ln corresponds to the phase or gives the phase delay. Now if we observe at port 1, as we can see at port N, I had initially this port N. Now I am moving away from it. I have this extension by a length Ln. Now how is this An dash related to An? Using the similar logic that we use for a lossless transmission line, I can say that An would be An dash e to the power minus j beta ln. And I can also say bn dash would be the same, would be bn, same amplitude, and then a phase delay of e to the power minus j beta ln. Or in other words, I can say from this equation, if I name it as equation 1, if I name it as equation 2, from equation 1 I can write, from 1 I can say an dash is equal to an e to the power this minus j beta ln. When I take it to the other side, it will become plus j beta ln. So therefore the ratio, therefore SNN dash, which is the ratio of bn dash upon an dash, becomes bn dash is this thing, bn dash is bn e to the power minus j beta ln, and an dash is an e to the power minus j beta ln. Now bn upon an, if we can see, bn upon an is nothing but snn. bn upon an is snn e to the power, see, an dash is an dash e to the power this, that means an dash is this thing, e to the power plus j beta ln. I have to write here plus. So when this goes up, so SN, bn by an, as I said, is snn, then e to the power minus j beta ln, this plus j beta ln would again be j beta ln. So I have snn dash is snn e to the power minus 2j beta ln. So the s parameter snn dash is same as snn, except that it is being multiplied by some quantity e to the power minus 2j beta ln. And this is what this property means. If any of the terminals, ports, or reference planes is moved away from a junction by a distance ln, then each s parameter involving that n would be multiplied by e to the power minus j2n. What it means is involving that port. This part is important. I'll try to explain it again. Involving that port. So involving that port would mean, say for example, if I am moving port, if I am extending this port n by some distance ln, then 1n will change, 2n will change, 3n will change, all those which involve n. S13 would be same, S212 would be same, S21 would remain the same, S13, S34, S43, all these parameters will remain same except the parameter involving this port n. As I said, S3n will change, S2n will change, S4n will change, etc., etc. They all will change so far as the ports, or so far as the S parameters involving port n are considered. So this is all we have in this lecture. Thank you.